Hello my dear students, welcome to the session. Last class we discussed the problem number 14. Now in this session let us have a discussion on problem number 15. Okay, so let us read the question now. All of you please look at that problem number 15 in classroom workbook. When a periodic triangular voltage of peak amplitude of 1 volt and frequency of 0.5 Hz is applied to a parallel combination of 1 ohm resistance and 1 farad capacitance. The current through the voltage source has waveform dash. A blank is given, but here the four options are given. Okay, so first one is what actually here, a rectangular pulse. Okay, and the second one is what option B is given, sawtooth waveform. Okay, triangular but sawtooth waveform. C, there is a combination of these two actually. D is also combination of these two. Okay, so if you look at the waveforms given, option A, what is option A? A rectangular pulse. Okay, all of you please look at that options given. B, sawtooth waveform. Okay, sawtooth waveform. C, okay, something like this. Some combination of the rectangular and triangular. But it looks same, but only thing this is decreasing and option D is like increasing. Okay, so it's something like this. Okay, something like this. Something like this. Okay, so now if you look at this, all of you, the four options, if you go through it, you will understand clearly that when you have the total current, what is actually total current here? Total current is nothing but this IR of t and IC of t. Okay, IR of t plus IC of t is nothing but what? Total current, I of t. But what is IR? IR is nothing but the total voltage by total resistance. I mean resistance here, total voltage by, because directly appearing that voltage. R. This will also give you a triangular waveform. Okay, triangular waveform. Triangular waveform. Now here if you see the IC, what is IC actually here? IC is nothing but C dV by dt. So what you get here? Since it is triangular waveform, when you differentiate it, see this is ramp. When you differentiate this, you will get step. That means what? You get a rectangular waveform. Yes or no? Rectangular waveform. Now what's happening here is when I of t is taken, both combination of these two, okay, you will get the combination of these two. You neither get the rectangular nor a triangular or whatever related to triangular. That is nothing but, you know, the sawtooth. So these two options can be directly, okay, removed, and you are left with only two options. Now here the point is, now this is decreasing and then increasing, whereas here this is increasing then decreasing, something like this. So you have a combination of both triangular and rectangular, that we have to choose one of these, C and D. It is easily, you know, observed from the given four options. Understand all of you? Okay, so for that what we try to do is we just draw first of all the, you know, current flowing through the resistor, then we draw current flowing through the capacitor, then we superimpose, then we understand easily what kind of waveform are we getting. Okay, so let us see first. Okay, this one is a waveform of current through resistor. Okay, same you will get because of the reason VR of t by r, sorry, V of t by r. Now, every point on this particular waveform is divided by resistance. The resistance value is 1. Therefore, you get same as it is waveform, right? So, therefore, IR of t. What about this? This is plus 1. What about this? This is minus 1. Now, here, this is 0.5. Now, this is 1. This is 1.5. This is 2. Now, the time is in seconds, let us say. Now, what you get here? The IR of t is the same as it is whatever you have V, right? Now, let us try to draw the waveform of the current through the capacitor. Current through the capacitor, IC of t. What is IC of t actually? To draw that IC of t, this is nothing but what actually slope. Yes or no? Slope. Slope into capacitance. What is the slope of it here? The slope is, you can see, 1 by 0.5. 1 by 0.5 is nothing but 2. Now, 2 into C will give you IC, but C is already 1 farad. But the slope is here 2 volts per second. Now, the current will become IC, okay, will become, okay, the capacitance is 1. Now, this is the slope into 2. Again, you will get 2 amperes. So, this is going to be 2 amperes. This is going to be now, the slope is also here. You can observe. Slope is minus 2, okay, volts per second. This is slope plus 2 volts per second. This is an increasing slope. This is a decreasing slope. Negative slope, positive slope. This is also positive slope. Yes or no, all of you, okay? So, therefore, you get now here, if this is 1, then this is also 1, okay? This is also 1, let us assume here. And you get now let me take the scale here a little. This is 2. Understand? Okay. Now what do you get here? This is actually 0.5. Okay. Let me draw it clearly once again because I need to manage the space. All of you, just please observe clearly because I need to superimpose and manage the space. Now look at this. This is t second. This is 1 and this is 2. Let us say IC of t. This is minus 1 and minus 2. What do you get here? Let me draw the waveform. 1. Is it 1 or 2? Yes, 2, right? So let me draw 2. Let me draw 2. This is 1. This is 2. IC of t. Minus 2. Yes or no? Minus 2. Up to this point. And then you have, okay, this is something like this. It goes. Because if it is increasing up to this point, then this will also go up to this particular point. What is the 2.5, right? Up to 2.5 it will increase. Up to 2.5 it will just maintain that. So 1, 0.5, 1.5 and this is 2. It goes up to this point, right? Okay, it's something like this. It's something like this up to this point. Well, now let us try to understand superimposing these two. Okay. You can also see in the negative direction, it is also coming from the negative, right? But it is the increasing slope up to minus 0.5. You can see from this particular point, okay? What is this actually here? 0.51, but minus 0.5 is a minus 1, right? So it is coming from this particular area. Good. So this is what actually the waveform you have. Just for better understanding purpose, I have just extended here. Now let us try to take this is 1, this is 2, this is 3. Understand? This is I of t now. Okay? From this itself we will understand clearly that this is plus 2 and here it is raising. That means what? From 0 it is raising. Yes or no, all of you, okay? From 0 it is raising. Now when it comes to 0.5, it is coming down to -2. Yes or no, all of you? Coming down to -2. Then here it is decreasing. Yes or no, all of you? That means what? Here negatively increased. Then again positively increased. Then negatively increased again. So what is happening? Clearly understood that it is from 0, it is increasing, then coming down instantaneously from that value to some other value, then negatively increasing, then again instantaneously it is rising up to certain point, then positively increasing. Like this, what's happening? Option D is already understood clearly, but still, just I'm extending the explanation here. You got the answer, but you need to really understand clearly with all numericals. For that sake, I'm just trying to explain elaboratedly. Okay, try to look at this. So 1 plus 1 plus 2 and plus 3. Now -1, -2 and -3. Understand all of you? Okay. Now look at this, all of you. Okay. This is 1, 1.5 and then 2, right? All of you, okay? Look at this. When you add both of them, you see how you are going to get. When you add both of them, you see how you are going to get. Now, I of t, that I of t can be written as what? I of, let me calculate here. I of 0. What is I of 0? Look at this. I of 0 is nothing but what? I r of 0, nothing but 0. Okay? Nothing but 0. 0 plus. What is IC of 0? Nothing but 2. Yes or no? So what do you get here? Plus 2. That means you have the value over here. This is the point. Understand? Okay. Now, next. Even if you take I of 0 minus 0.5, what will you get? I of minus 0.5. Tell me all of minus 0.5. If you go with that, okay, just for better understanding purpose, what do you get here? I of minus 0.5. This is actually -1. Okay, this is actually -1. And this one you get what? Plus 2. Okay, -1 plus 2. So what do you get here? Plus 1. So what do you get here? Plus means what? Okay. Now in the negative portion, you see here, this one if you extend, okay, negative portion, you get what? This is plus 2 and this is -1. So what do you get? Where does the point starts actually here? This point starts somewhere here. Yes or no? Okay. This point starts somewhere here. Now I of 0.5, if I calculate, what will I get? Tell me all of you. I of 0.5. What is I of 0.5 here? I of 0.5, this IR is actually changing. I mean, the value of this IR of 0.5 is plus 1. But what is IC of 0.5, Nana? This is plus 2 to minus 2, it is coming down. So, if it is plus 2, then plus 1, then it is plus 3. 2, this is plus 1, but changing up to what? Minus 2 instantaneously. Minus 2 plus 1, nothing but -1. It is changing from plus 3 to -1. I hope you understand the point when I'm adding the 2 points. This point added, therefore you got plus 3. This point and this point. What is this? -2 plus 1, nothing but what? -1. So plus 3 to -1, it is changing. So we will show that in the diagram later on. Okay. Now, that means can I show like this? It is 0.5, right? 0.5. It is going up to what? Plus 3. Okay. Then it is changing from plus 3 to what? -1. Can I say here something like this particular point? Yes, I can. That means it is something like this. Okay. That's it. I hope you understand the point. Okay. Now here, I of 1, let us take. It is just only, for better understanding purpose, I'm explaining. Actually, you got the answer. Don't worry about that. But tomorrow in GATE, you may be asked the questions in different dimensions. Everything what we learn, we should learn completely, with all fundamentals, with all concepts. If you have that clarity, tomorrow, if the question is also altered in any dimension, you'll be in a position to answer that question. Okay, that's why I'm just elaborating. Okay, now look at this, I of 1. What is I of 1 actually here? I of 1, this IR of 1 is 0. But what is IC of 1? Nana? -2. So -2 plus 0, it is -2, that's it. So it is 0, okay, -2. Nothing but -2. Now what is, that means what? -2 means what? You are going to get what? Up to this particular point. So you are having this particular point, okay, -2. Now look at this. That means can I draw like this? Can I draw like this? Yes, I can. Yes or no? Okay. Now look at this. I of 1.5. What is I of 1.5? I of 1.5, you can see here, this is -1. But whereas this one is what? -2. 2 plus 2, it is changing. So when it is -1, it is changing from -2. That means what? -3. -3. 2. It is +2, but -1. What is the result? +1. 2 plus 1. So it is changing from -3 to +1. That means you can see here, the value of I of t is going to what? Become what? -3. -3 here, -3. Okay. What is this? Up to this particular point, it is nothing but -3. That means you can extend up to this particular point. Okay. And then it is going up to what? Okay. Then it is going up to what? +1. That means this one. Okay. This one. This one. Right. So therefore I got up to this particular point. Right. Up to this particular point. Now hereafter, I of 2, let us see now what's happening. I of 2. What is I of 2? IR of 2 is 0. But IC of 2 is a 2. Okay. So 0 plus 2, you get what? +2. Yes or no, all of you? Okay. Then what are you getting here? So here you are getting, okay, here you are getting, in case if you really go from, to 2.5 also, what do you get 2.5? Tell me all of you. 2.5 means again up to what? +1 it goes. Okay. So now if you just extend up to 2, okay, up to 2, this particular point, this goes to, of course, it will be increased further if you go up to 2.5. Understand all of you? Okay. Now, where it is started actually here, it started at 0 if you take it as a reference. It started with 2. But if you take minus 0.5 as a reference, it started with what? +1 only. That means it started something like this. So the waveform goes like this. Look at this. If I take this as a starting point, it is increasing. Okay. +1 to +3. Then +3 to -1 sudden drop. Okay. -1 to -3. Then -3 to +1 sudden rise. Now -3 to +1, then +1 to again +3 it goes, because I'm not going up to 2.5, right? Here I have shown only up to 2, but if I show up to 2.5, it goes up to +3. Then again it falls down to what? -1. Then -1 to -3, -3 to +1, +1 to +3. Like this it is going on. Understand all of you? Okay. So it's very clear that it is changing from +1 to +3, then +3 to -1, -1 to -3, -3 to +1, +1 to +3 again. It is something like this, getting repeated. It's a periodic waveform. It is already clearly mentioned, a triangular periodic waveform. Then you are going to get this particular waveform. Understand all of you? Okay. So I've just elaborated actually here. You don't require all these things to answer this question, but I'm telling you for the sake of knowledge. Okay. Because tomorrow we don't know which dimension the question is going to come in the exam. We must be ready for everything. If we understand the superimposing of the two waveforms and constructing another resulting waveform, then you can answer any question that you come across. So please draw it clearly. I'll give you sufficient time. Please note down. I'll give you some 3 minutes time to note down this. Please go ahead. That's a very interesting problem. Please note down. Option D is correct. Looking at the shape of that waveform, option D is correct. So if you go further here, Okay, it will also go further here. It will also go further here like this, up to again this 3. Okay, so it's very clear. It's ready to increase. It's a combination of triangular and rectangular. Okay, simply by superimposing. So first instant itself we can understand it is 2, it is 0, from 0 to 1 it is raising, but it is constant. That means what? From 2 to, okay, plus 1, no, therefore 3, from 2 to 3 it is raising. That is very clearly understood already. From that itself we can understand the option D is correct. But still, just for superimposing and drawing the whole diagram with all numericals, I've just done some calculation here. Okay, please complete it quickly. Hope you have done this particular part. Okay, I'm just removing only this particular part. Only this particular part. Okay, you please carry on with that. Okay, let me take 16th problem. Problem number 16. All of you please quickly note down the earlier problem. The 16th problem was also asked in GATE. 15th and 16th both were asked in GATE, previous GATE question. Okay, so I think all of you might have done that. Let me read the question 16th one. A square wave shown below is applied across 1 millihenry ideal inductor. The current through, full stop, okay, the current through the inductor is dash wave of, again one more dash, peak amplitude. That means he's expecting what kind of waveform it is. And after knowing the waveform, what could be the peak value of it? You know what is the meaning of peak value, okay? So the square wave shown below is applied. What is the square wave actually shown here? This is what the square wave shown below, right? So let me draw it. This is actually V of t, 1 volt, minus 1 volt, 0.5, 1 volt. T is in millisecond, okay? So this is applied to what? A 1 millihenry ideal inductor. Okay, ideal means you know that there is no resistor component. Okay, so now what is expecting? The current through the inductor is dash, he's saying. Okay, the current through the inductor is dash. So let us try to answer it easily. That what is actually when voltage is given and we need to find current through the inductor, what is the formula that we have? Current through the inductor is, okay, I of 0 plus 1 by L integral 0 to t V of t dt. This is actually, you know, 0 because he did not mention anything about. Did he mention anything about the initial current? No, no information is given directly or indirectly. We can assume it's 0. But we can take this one as, okay, area under V of t. Yes or no? We can go for the integration also. But since we have a well-defined waveforms, the square, we can easily find the area, okay? But divided by L from 0 to t. That's it. So how do you find the current? Now current, let us find, okay, at 0 already, let us try to find at 0.5. 0.5 if you find, what will you get? Tell me. What will you get? 0.5. That means what? I of 0.5 is nothing but I of 0 plus area under from 0 to 0.5. Yes or no? But already I of 0 is 0. Therefore, area is how much actually here? The area, what you got here is of A1, let us say. This is A2, let us say, and this is A3. It is going up to, we don't need that actually, that part. So A1, okay, divided by L. But what is A1 actually? 1 into 0.5 divided by, what is N actually? 1 millihenry. Okay. 1 into 0.5 into millisecond, that is 10 power minus 3. Because 0.5 into millisecond divided by 1 millihenry, 10 power minus 3. So finally you got 0.5, okay, amperes. Yes or no, all of you, okay? 0.5 amperes means what? Where is it actually 0.5? On the same scale, if you take current also here, I of t, same scale, if I take 1, okay, and this is volts and this is in amperes, then what do you get here? This is 0.5, yes or no? So this is 0.5. Now, I of 1, I would like to go. I of 1 is what actually here? I of 1 means A1 plus A2. Yes or no, all of you, okay? So A1 plus A2, no doubt, by L. What is A1? Already you got 0.5 plus what is A2 actually here? Minus 1. This is plus 1, this is minus 1. Duration is same. Again 0.5 to 1 means again here 0.5 only. So what do you get actually here? You get minus 0.5 by 1. Okay. So finally you get what? 0. 0 amperes is the current at this particular instant. So you get here. Now if you join all this, how do you join? Because you know, when you integrate the step function, you get a ramp. Yes or no? So therefore, ramp is nothing but it looks like this. So what you're trying to get here, you are getting what? A triangular waveform. For the triangular waveform, for this particular case, what is the amplitude you got already? 0.5. So the first blank indicates triangular waveform, and the second blank you can write it as what? 0.5 amplitude is the correct answer. So please note down that quickly. Very simple problem. Let me take this off. Quickly note down. Okay, now let us look at, okay, I think all of you are done with this 16th problem. 16th problem, now let us look at the 17th problem, okay. 17th problem, let me read it. 17th problem. The number of 2 microfarad, 400 volt capacitors needed to obtain a capacitance value of 0.5 microfarad rated for 1600 volt is. Understand? Okay. So I think you understand. Here, if you take 2 microfarad, okay, comma 400 volts, right? Each one is what? 2 microfarad comma 400 volt. Now you want to take these capacitors, individual capacitors, in a number such a way that the total capacitance value must be how much here? 0.5. The total capacitance value must be 0.5 microfarad, and rated the total voltage how much actually here? 1600 volt. This is the combination actually would like to take. Now the combination of different capacitors are required to get 1.5 microfarad comma 1600 volts. Understand all of you? Okay. Very simple question. How many are there? Then how many are required here is asking. What is this actually? 12, B is 8, C is 6, D is 4. These are the options given. So let us try to answer it easily. We can easily answer this question. Look at this, all of you. See, you can go for the combination of series or parallel. But usually when you go for a series combination, the effective capacitance will decrease. When you go for parallel combination, the effective capacitance will increase. Yes or no, all of you? When you go for series combination, the whole combination voltage rating will increase. When you go for parallel combination, the voltage rating remains same. Because for parallel combination, the voltage is same. Yes or no? But look at this, each individual capacitor is having the voltage of what? 400 volt. But you want the total voltage of 1600 volts. That means you need to increase the voltage. Increase the voltage means you must go for the series combination of capacitors. Yes or no, all of you? Okay. Well, but when you go for the series combination of capacitors, the capacitance value will decrease. Yes or no? How many capacitors are required actually to get 1600 volts to be connected in series to get 1600 volts? Definitely 400 into 4, total 4 capacitors are required. Yes or no, all of you? Okay. So therefore here let me draw it clearly. Let me draw it clearly. 4 capacitors required. So first I got voltage rating. Voltage rating how much here now? 1600 volts. 1600 volts. This is between let us say some AB terminals, let us assume. What is the capacitance value of each capacitor? It is 2 microfarad. When you go for series combination of n number of capacitors, the C equivalent become what? C by n. Yes or no? But now here 4, therefore 2 by 4, how much it is? 0.5 microfarad. That means now the whole combination will give you 0.5 microfarad, comma voltage rating is increased because each capacitor is having withstanding capacity of 400, 400 plus 400 plus and so on, you get 1600. Okay, well and good. Now I met the requirement of voltage rating, but I need to meet the total equivalent value of the capacitance 1.5 without changing the 1600 volt rating. Yes or no, all of you? So without changing voltage rating, can you increase the capacitance? Is it possible or not? Yes, it is possible, but you have to go for parallel combination. For effective capacitance value, okay, to be increased, you have to go for parallel combination. Anyway, when you go for parallel combination, the voltage rating won't change. For that reason, let us go with the similar kind of, okay, branches. How many you require? 0.5 is there. C equivalent will be there in the case of, this is a series combination. Okay, for a parallel combination, C into N. Okay, but how much you require here? 1.5. Each one is how much? 0.5. How many are required in that particular section? Okay, N is equal to how many? 1.5 by 0.5, that is 3. Like this, you need 3 sections. Okay, that means 3 sections you require. Okay, now each section is offering. I've just calculated number of branches to be connected in parallel. How many branches required? 3 branches are connected in parallel, but each branch consists of how many capacitors? 4 capacitors. Okay, 4 capacitors. So finally 4 capacitors in each branch, okay, into 3 branches, 3 into 4, you got an answer of 12. Understand all of you? Okay, so this is how you need to answer the questions. Okay, so very simple one. Note down all of you. So now you got the effective capacitance. How much? The effective capacitance when you take here, when you take effective capacitance, okay, you got now C equivalent is 1.5 microfarad. Okay, 1600 volt. That's it. This you take now between these two. But each one is of 0.5 microfarad, comma 1600 volt. 0.5 microfarad, comma 1600 volt, each one. So you're adding these two and getting that value. There's another interesting question. Question number 18. It was asked in GATE. Very interesting question it is. Read that question, all of you. Three capacitors C1, C2, C3, whose values are 10 microfarad, 5 microfarad and 2 microfarad respectively, have breakdown voltages of 10 volts, 5 volts and 2 volts respectively. For the interconnection shown, the maximum safe voltage in volts that can be applied across the combination and the corresponding total charge in microcoulomb stored in the effective capacitance across the terminals are respectively. It's a very interesting question. Look at this, all of you. What is the combination given here? This is what the combination given, right? This is C1, it is 10 microfarad. This is C2, how much it is? 5 microfarad. This is C3, this is 2 microfarad. Now these are the AB terminals given. So what is expecting actually? Here it is, its breakdown strength is of 10 volts. Here the breakdown strength of this one is 5 volts. Here the breakdown strength is how much? 2 volts respectively. Understand, all of you? So what is the maximum safe voltage that can be applied across the combination, that is AB? Okay. That means so that every capacitor is going to be safe. Okay. You know that when the voltage increases, okay, the stress on the dielectric will increase, and if that voltage hits the maximum dielectric strength of the capacitor, then the capacitor will be damaged. Yes or no, all of you? The dielectric gets punctured and finally the capacitor gets damaged. So let us see now what is the maximum safe voltage that can be applied. See, whenever this kind of problems are given, maximum safe voltage that can be applied, you must always follow certain logic. Okay. Some 4 options are given. Out of 4 options, yes, definitely, I'll give you the 4 options here. Out of 4 options, you can easily find them. But without using 4 options, nowadays in GATE, you know very well, fill in the blanks are asked. Yes or no? So what happens when blanks are not, what happens when options are not given? So we must be ready for answering the question even without options sometimes. So be careful here, okay? If you go trial and error approach, like first I apply 2.8 volt. Let me see whether every capacitor is operating safe or not. That I can check. If 2.8 is not safer, okay, then what will happen? I go for, first of all, maximum safe voltage. That means 7 I apply. If I apply 7, if any capacitor is found to be damaged, then what is the next option? Only 2.8. Already you have 2.8 2 options, 7 2 options. If 7 is not working, then what is the other option? The 2.8 only. That is the maximum safe voltage. For that maximum safe voltage, what is the charge is asking? That means what? You can find the total capacitance into that maximum safe voltage. Q is equal to C into V. You can get the charge easily. That means from the back substitution process, from the 4 options, you can easily answer this question. No doubt in that. Understand, all of you? So what will I do? Tell me, all of you, from the 4 options. First I apply 7 volts. Let me see if any capacitor is damaging or not, because maximum safe voltage is 10 here. Then if you apply 7 volts, this is safer, but we have to check whether any capacitor is getting damaged or not. Understand, all of you? Okay. If any capacitor is damaging, then this 7 volts is not applicable. So 2 options are ruled out. Then other 2 options are left over. Then obviously 2.8 is the safe voltage. For that 2.8 volts, the total C equivalent you can calculate. Now Q is equal to C into V. You can multiply them. You will get the charge corresponding to that particular maximum safe voltage. But this is not the way we answer the question when 4 options are not given. Yes or no? What we do now here is, let us see. Let us assume that the maximum safe voltage, okay, V be the maximum safe voltage. Understand all of you, okay? Maximum safe voltage. Look at this, when you apply that maximum safe voltage, no doubt that must be less than 10 volts. Forget about these options, okay? No doubt that is less than 10 volts. Now, if I apply that voltage, what will happen? This is safer, no doubt. But these two capacitors are connected in series. For this series combination, if I apply some voltage V, okay, if I apply some voltage V, the same voltage is appearing across this also. This is already safer, no problem. But now I am worrying about C2 and C3. Now, when elements are connected in series, okay, that capacitor are connected in series, you can easily understand that which capacitor is going to be under dangerous zone. Easily you can do. How it is? Let us see. Q is equal to C into V. For series combination, Q is same. We already studied. Then what will happen here? V is inversely proportional to C. Now, a capacitor with lower capacitance will experience, okay, higher voltage. Will experience higher voltage. This is a simple concept. Okay, so who is actually now in in problem now in this C2 5 microfarad, C3 2 microfarad, when the two capacitors are connected in series, who is actually have a problem here? A capacitor which offers lower capacitance. Yes or no, all of you, okay? Now 2 microfarad capacitor is in having some problem. If you really work for that 2 microfarad, if you can really design that maximum safe voltage, keeping in mind this particular capacitance, then obviously the other is also taken into consideration or not? Yes, definitely. What is this breakdown strength actually here? 2 volts. What is this breakdown strength? 2 volts. That means whatever you apply the voltage here, okay, whatever you apply the voltage here, after division of the voltage across this C3 should not really cross this 2 volts here. Should not really exceed the 2 volts. I hope you understand the logic. See, when the two capacitors are connected in series, I am worrying about the capacitor which offers a lower capacitance according to this concept. Understand all of you, okay? Now, what is the maximum allowable voltage of this particular capacitor? Because already breakdown strength is given, 2 volts. Now, you apply any voltage that you want, maximum, highest value, such a way that the voltage across C3 is not exceeding its breakdown strength, that is 2 volts. That means the V3 value is known now. For that corresponding, the maximum safe voltage can be calculated or not. It's simply a reverse calculation. That means, look at this. Now I apply VC3 is nothing but what? That is C2 by C2 plus C3 into the maximum safe voltage. This is the maximum safe voltage. This is an unknown value. This is a known value. Why it is known value? Because what is the breakdown strength? 2 volts. That means you can apply up to 2 volts. Understand all of you, okay? So therefore, I take it as the 2 volts here. Now corresponding to this 2 volts, what could be the value of this maximum safe voltage to be applied across the combination of this C2 and C3? I can easily determine. Understand all of you, okay? So what I take here is V is equal to, what is C2 plus C3, Nana? That is 2 plus 5. 2 plus 5 by, what is C2 here? That is 5. That means 7 by 5 into, what is this actually you got? Into 2. 14 by 5 volts. I hope you understand this. So 5 2 ja, okay, 5 8 ja. That means 2.8 volts. 2.8 volts is the maximum safe voltage that can be applicable or that can be applied across the combination. The same voltage will appear across this. Don't worry, because already it's 10 volts, whereas you are applying only 2.8 volts. If you apply beyond 2.8 volts, okay, these two are safer, but this is not safer. Understand? Now, corresponding to this, the total equivalent capacitance can be determined. What is that actually here? C2, C3, that they are in series. What is that value? 5 in series with 2 and then parallel with what? 10. So 5 into 2 by 5 plus 2. Okay, plus 10, because parallel combination capacitor, you can add them. So what is this? 10 by 7 plus 10. So what is 80 by 7? It is microfarad. So what is actually QT is nothing but 80 by 7 into, that is 2.8. So 7 4 ja, that is 0.4. Okay, 4 8 ja, 0 0 cancel, 32. Okay, 32. That is volts. This is microfarad, therefore microcoulomb. So you got 32 microcoulomb. Okay, this is 32 nana, this is not 3.2. 32 microcoulomb and 2.8 is the correct option. So see, I have not I have not taken the help of the 4 options. I have directly attacked the problem. Remember why I am explaining this one, because tomorrow you may not be given 4 options. You may have numerical type of questions. In GATE, you have 40 to 50% of the questions are from numerically answered type. NAT, numerically answered type. Okay, a blank is given and a virtual window is provided in the online platform when you take the exam. Okay, then you have to enter that answer in the virtual platform. A keyboard is available. In that keypad, you can answer the question, you can choose the answers. So therefore, my dear students, you must be very careful while answering the questions. If you learn the concept, okay, then you can answer the question in any dimension if it is asked. What is the concept that we are following here? Maximum safe voltage means, especially when the elements are connected in series, you have to take the capacitor which is offering the lower capacitance into consideration. If you take that capacitor into consideration, that means you are considering all capacitors into consideration. Yes or no, all of you? The capacitor which is in danger, if you consider, then the other capacitors can also be considered, obviously. That is why out of this 5 microfarad and 2 microfarad, I have taken this 2 microfarad only because the voltage is inversely proportional to C. The voltage, higher voltage will appear across the capacitor which offers the lower capacitance. So I worked on that particular capacitor and finally I got the answer here like this. Okay. So please note down this very interesting question. With this, some problems that we have covered almost, I think, 18 problems on inductors and capacitors. Variety of problems we have touched already. Understand all of you? Okay. So based on this, you can even answer any question that you come across. I stop the session here. We'll see in the next session the remaining things.